Good day, everyone. Thanks for tuning in into my presentation. I will be talking about controlled light-driven levitation of macroscopic plates today. I'm going to leave the abstract here for a few seconds. Feel free to pause the video and read through the abstract. You can also find the citation at the bottom. Feel free to check the paper out. Okay, so I'm going to start the presentation by showing you a video. This video has been taken in a 60 Pascal ambient pressure environment. And the disk that you are going to see that flies in this video has a diameter of 1 centimeter, and we are shining light from underneath of this disk. Okay. As you can see, the disk hovers over an area, and I have cut the video short. The video is long, so you're only seeing the first 20 seconds. Okay, so what you saw here essentially is a new way to fly. We have used a very old mechanism to create a new way to fly macroscopic objects. And I'm going to discuss this more today. All right, so in order to look at why we actually came up with this new way of flight and levitation, we have to go back to the mechanisms that we have and the ways that we can actually fly. If you look at the Earth's atmosphere on the right side of the screen, you can see that there's a range of the atmosphere between 30 kilometers and 80 kilometers that also includes mesosphere. We call that near space. In this region, we really don't have any mechanisms to fly a device for a long period of time. It is stretched across, again, 30 kilometers and 80 kilometers, and the pressure ranges that it translates to are seen in this plot. And if you remember in the video that I showed you earlier, the pressure of the environment was 60 Pascal. So that 60 Pascal roughly sits here, okay? Somewhere between 50 and 60 kilometers, which again, we do not have a mechanism to fly in. So that's why it's essentially a new way to fly. Why is it important for us to be able to fly in this region of the atmosphere that we call near space? Several reasons. Well, first, we don't have any flight mechanisms, and it's a region of our atmosphere that has not been studied. That region is very important because it involves, it has a lot of information about weather patterns that we can use to improve our models of weather patterns. We can also use the different mixtures of gas and other things to be able to sense in this region of atmosphere. And of course, there's always surveillance applications that we can do. This region is really inaccessible because the pressure is too low for aircrafts and balloons, and it is too high for satellites and causes a lot of drag. Okay, so this new way to fly, which is also a mechanism that has been around for a while, is called photophoresis. Photophoresis translates to light-driven flow. And the force that comes from that light-driven flow is called photophoretic force. Okay? This photophoretic force has been studied for over a century over microscopic particles. The way it works is that if you have a microscopic particle and light shines on it, one side that absorbs light gets hot, and the other side stays cooler because there's a finite conductivity across this particle, right? And the way that the force is created depends on which pressure regime that we are operating in. In the free molecular regime, where Knudsen number is above 10, aka mean free path of the gas molecules is 10 times larger than the characteristic length of our sample, what we see is that the individual molecules do not interact with each other. So when we have this unevenly heated particle and the individual molecules hit either side, the molecules approach the sample, approach the particle with the same velocity because they're coming from a uniform temperature ambient. And when they hit the surface, they absorb different amounts of heat because the surface on either side has different temperatures. And the molecule that absorbs more heat on the hotter side bounces back with a higher velocity and creating a net force on the particle. In this slip flow regime, the continuum regime, however, things are slightly different. In this regime, the layer of the gas that is the closest to the surface of the particle, that we call Knudsen layer, heats up unevenly. And that is exactly because the particle itself is unevenly heated. And this uneven heating in the Knudsen layer gas results in what we call thermal creep, which essentially creates a force on the particle. Okay, so what we wanted to do is that we wanted to not only use particles, we wanted to actually be able to fly large scale, centimeter scale samples in upper atmosphere. And so we needed larger diameters than just microscopic particles. The challenge with that is that if you want to create something that is large in X and Y and still has this temperature gradient inside it, your structure becomes too heavy. And the force is not that high to lift off this heavy structure. So what we wanted to do is that we wanted to make the device as thin as possible so that helps us with the weight. But the problem that poses is that we no longer have this temperature gradient inside. So we approached our problem by assuming that we're just going to eliminate the need for the internal temperature gradient. And what we wanted to focus on was the difference in the temperature of the sample, average temperature of the sample, and the ambient temperature. Because in high altitudes, we also get the benefit of having a low ambient temperature. Okay, so these two were in our mind when we wanted to approach our new flight mechanism. And we came up with a thought experiment. We said, okay, if we have a very, very thin disk that essentially has zero thickness mathematically, and it's large in X and Y, and we submerge this disk in a low pressure gas environment where the molecules do not interact with each other. If we shine light on the disk and assume that the disk absorbs light and heats up, it heats up to let's call it a certain temperature that is almost the same on both sides because we assumed a thin disk. And the ambient temperature is fixed everywhere. And now what we focused on is this coefficient called thermal accommodation coefficient. And what that is basically an indicator of how much energy is transferred between the gas molecule and the surface. And the way you can write it, we can think about it, is that if we have a molecule gas molecule approaching the surface, hitting the surface and bounces back with a characteristic temperature that is related to the ambient temperature, to the surface temperature, and this coefficient called accommodation coefficient. So essentially, the characteristic temperature of the bouncing molecule is related to the accommodation coefficient. So if you want to change the velocity of the molecule that bounces back, aka its temperature, we can essentially change the accommodation coefficient. And that's what we thought about. If we have two different accommodation coefficients on the two sides, we can have two different velocities of the bouncing molecule, which essentially results in a net force. And because that force is created due to difference in the accommodation coefficient of the two sides, we call it delta alpha force. So this is the concept in the low pressure regime. On the other hand, in the slip flow regime, when the pressure is high and the Knudsen number is low, we still have the same definition of the accommodation coefficient, but we no longer have that individual molecule interaction. Rather, we have, as I said, this Knudsen layer that heats up unevenly on either side of the disk. So what happens is that we have unevenly heated layers of gas close to the surface, and that results in the thermal creep. But this thermal creep happens across essentially a zero thickness, mathematically zero thickness disk, which creates all sorts of discontinuities and jumps that we cannot really easily formulate. So what we did, and you can read about it in the paper that I cited earlier in the video, what we did is that we avoided the discontinuity by first assuming an oblate spheroid and assuming there's a difference in the accommodation coefficient of the two sides, and finding the temperature gradient in the Knudsen layer around this spheroid. Now we can find the thermal creep without any discontinuities. And then we took the limit of this large radius over a small radius over the large radius go to 0. And essentially we found our physical problem through this step of mathematical problem solution to the discontinuity. Okay, great. So we approached the two different regimes, premolecular and disciplinar regime, with these two different mathematical basics, and we found the formulas. Again, the formulas are written in the paper. You can go ahead and take a look at the paper if you'd like. Here, I'm just going to skip over the mathematics of it and get to the experiments. So what we wanted to do is we wanted to create samples and test this mathematical model that we just presented. And we wanted to create samples in a cheap, fast, and easy way. Now, if we want to make samples, there's one thing that we must have in mind, and that is this difference between the accommodation coefficient of the two sides, because that is essentially what creates the force for us. Okay. Now, what we wanted to do is we wanted to change the accommodation coefficient. We wanted to be able to control the accommodation coefficient. There are ways to do that. The easiest ways that came to our mind is that first, change the interaction time between the gas molecule and the surface. If a gas molecule spends more time closer to a surface, it absorbs more energy from it. Second one was to increase the number of collisions a gas molecule has with the surface. And we call that creating a trap. We sketched this schematic diagram, and we essentially thought if we have a smooth surface on the top and a structured surface on the bottom, in a way that on the smooth surface, we only have one collision per molecule, and on the structured surface, we have on average more than one collision per molecule, we should technically get a lift force. The challenge now, or the next step I should say, was to actually create this conceptual design. And what we did, we started with a 4-inch wafer. We stretched a 0.5 micron thick mylar sheet on top of this wafer, cheap, commercially available mylar. Now this, keep in mind that this sheet is only 0.5 micron thick, so it's extremely floppy and does not absorb light. These two were the 2 points that we needed to take care of, besides the accommodation coefficient. Okay, so we drop casted a solution of water-based solution of carbon nanotubes on this mylar, and then we heat it up on a hot plate at 50 degrees. You can see an image of the 4-inch with the entire 4-inch wafer with the CNT covered mylar here. And the bonus points that we got, as I said, the mylar itself doesn't absorb light. And the whole idea of photophoretic levitation is to be able to absorb light. And the CNT layer does that for us. The second bonus point that we got from the CNT layer is that it increases the structural rigidity of our sample. And we checked and weighed our samples. The areal density is roughly 1 gram per meter square, which is light enough for levitating objects. Okay. Now back to the main problem in hand, which is creating that structured surface on the bottom and the smooth surface on the top. So we picked a piece of this mylar, put it under the SEM, and you can see the difference between the structured surface and the smooth surface. And if I zoom in on the structured part, you can actually see that we have indeed created the trap that we envisioned. And so the next step is actually seeing if it flies. And not only we want it to fly the structure, these samples, we want it to be able to controllably fly the samples. So we created a light trap. This light trap has 8 LEDs in a circular way, as you can see, and the intensity goes up to 10 suns. So pretty intense light trap. And the sample was placed on a 74% transparent metallic mesh as a launch pad. And we put our sample and the metallic mesh inside an acrylic chamber to be able to take a video. Okay, you can see the chamber here with the metallic mesh and the sample on top, and the LED arrays under the chamber from the outside. Okay. Next step that we did is that we made sure that we indeed have created the light trap, aka this potential well that the sample cannot easily climb and fly away. These are all measured values. And you can see that we have created this 15 centimeter disk area that we can potentially trap the sample in, and the intensity goes pretty high. All right, so the next step was just fire it up, see if it works. What you can see here is 2 disks of 6 millimeters inside a 30 Pascal environment under 5 suns intensity. You can see the disks lift off, fly around each other, bounce with each other every once in a while, and essentially deform enough under the intensity of the light, under the temperature that they have, because these are very thin plastic samples. They deform on the edges and essentially settle down. Okay, so what we did is that we took our theory, we plotted the areal densities that we can, by the prediction of the theory, we can lift off, and then we draw this line, or I should say this band, that is the areal density of the sample that we made. And then the radius of the sample, which is 3 millimeters, the disk was 6 millimeters. And then we occupied all of the points that we saw levitation happening and all of the points that we didn't see levitation happen. Now, the levitation didn't really happen because of 2 main reasons. One of them was that simply the force was not enough. We were not in the right pressure regime for the sample disks that we had. And the theory indeed predicts it very, very correctly, that in the parts that we shouldn't see levitation, we indeed didn't see levitation in the experiment. The other type of, I would say, not being able to see levitation is thermal deformation. There are pressure ranges and a couplet of pressure ranges and the radii that creates this thermal deformation in the sample. The samples would deform before they actually experience enough force to lift off. And you can see those points on the plot with the half circles here. I show you 2 of the examples here, and you can see indeed that the samples deform. Apologies. You can see that the samples deform under such conditions, and they will not be able to levitate. So not only the theory correctly predicted levitation where we should have had them, it also predicts non-levitation where we should not see levitation. Now that the theory is validated from multiple approaches, what we did is that we went back to our motivation to see if we can levitate these macroscopic structures in upper atmosphere, in near space. And what we assumed is that we looked into the literature and we found a reasonable difference between the accommodation coefficient of 2 surfaces that we can create without too much difficulty, which is around 0.5. We also took emissivity of around 0.5 because we also assumed that if you want to really fly in upper atmosphere, we can do surface modifications, again, easily doable, to reach emissivities of 0.5. And we assumed natural intensity of the sun because we didn't want to use an external man-made light source. We just wanted to use natural sunlight and see if with that natural sunlight and these conditions on emissivity and accommodation coefficient, we can indeed levitate structures, macroscopic structures in the near space and mesosphere band or not. So we found the areal density of the objects that we can levitate as a function of altitude and the radii. And we found that we indeed can use this new mechanism of flight for macroscopic objects, radii of somewhere between 1 centimeter to even 10 centimeters, to lift off not only the sample itself in high altitudes, but also payloads of up to 10 milligrams. We also check the temperature of the disk to make sure that the temperature doesn't get too high, so we can use simple fabrication methods, and the temperature indeed stays between 400 Kelvin for the ranges of the altitude that we are concerned. And the reason this is really the case is because of this low temperature of the ambient that indeed gives us a high temperature difference between the disk and the ambient, yet remains at the temperature of the disk remains cool, and that is because of this incredibly cold region in the atmosphere up there. So that works for us. So in conclusion, we created cheap, fast samples with a controlled accommodation coefficients difference on the two sides, and we successfully flew these structures at pressures that correspond to high altitudes in the atmosphere, where we don't have any other flight mechanisms. And then we showed with our validated theory, we showed that we not only can levitate microscopic structures under sunlight, we can also add useful payloads of up to 10 milligrams to these structures. Right? With that, I would like to thank the staff members of Sync Center for Nanotechnology, Nanocharacterization Facility, especially Meredith Metzler and Eric Johnson, and all of the co-authors for helping on this paper. Also, thank you for your attention.